Hey, I see you. How are you? Good. Now I'm crushing your head. So you know what they say about champions, it's hard to repeat because you get lazy and everybody comes after you. So let's not get lazy. Let's keep going and do some other tactics in our next season of volumes of a solid. Now we're going to look at cylindrical shells method. And so what we have is a nice little theorem here that says let F be continuous on the closed interval. Of course, that means it's integrable, where A is greater than or equal to 0. So we want to be on or to the right of the origin there for our closed interval. And we also want f of x to be greater and equal to 0. So anyway, it's on or above the x-axis for all x's in that interval. And so R is going to be the region bounded by the lines x equals a, x equals b, the x-axis, and f of x. And so what we're going to do is we're going to have a nice plane region right here. I've got an example, f of x equals x squared on 0 to 3. That's going to give a nice region R. That actually is the area. We figured out the area of this region to be exactly 9 square units using calculus back in a previous section. So we're going to have something like that depending on what f of x looks like. Then the volume we're going to obtain by rotating R about the y-axis. So basically we're taking that plane region, we're rotating it about the y-axis now and making a volume. We're going to actually be able to measure that volume, and it's going to be exactly equal to 2 pi times the definite integral from a to b of x times f of x with respect to x. And I'm going to use my little cylindrical scope here to show you why that's the case. So let's just look at this and let's try and visualize what's going on when we actually rotate this thing around. When we rotate it around, we're going to get something that comes all the way around. It's going to look basically supposed to be like a mirror image, right? Amber said this was good enough, so we'll go with that. My trusty assistant said, for me, that's pretty good. So don't erase it, just go with it. So we have that nice bowl shape, but what's happening is there's volume all around the outside. So it's almost like we got this big round thing with kind of a cup shape that's empty on the inside, right? That we could, pour some pop in there or something like that, or victory champagne from our championship, right? So, but you got to be old enough. Anyway, so coming back here, well, we've got this. So we could actually use this formula and figure out that volume, but what I want to show you is how we actually use this cylindrical shells method. So what we're really going to do is we're going to try and remember that that's all the way around, right? So what I'm going to do is I'm just going to pick a particular x in here, and I'm just going to do a little slice. And so if I do this in here, this is what it looks like, right? So basically I've got a slice in there. It looks like a cylinder, doesn't it? It would actually have a little width. So if you think of a pop can and you cut the top and the bottom off that pop can, there's just a little bit of width to that, right? And so we could actually try and figure up the volume of that. But what is the area, the surface area here, basically we can start at 0 and let our cylinder get bigger and bigger and bigger as we go, and the biggest radius of the cylinder would actually be 3, right? So let's kind of look at this and let's consider our spyglass here, this cylinder shaped deal, to be the blue cylinder that you see there. So I didn't quite draw it to scale. I should have drawn it in here, but just assume that it goes all the way to the back, and then we come over here, and then basically if I take that cylinder that we had here and then I open it up, what do you get? You get a rectangle, right? And so what do you know about the surface area of the cylinder? So I want to know what the area of this thing is. It's going to be the base times the height, right? Because it's a rectangle. So the question is, well, what's the base? The base is going to be, when you open it up, it's going to be 2 times the radius, right? So, but why do we only go from A to B then, and not from say, you know, in this case, -3 to 3, because I don't want to count stuff twice. So basically, when I start in the middle and go to the right, I don't want to, I'm adding up basically both sides of this and getting that area as we go and getting those tiny volumes based on the width. So we only need to go from 0 to 3, otherwise we'll count everything twice. But anyway, the question is then, what is the height of this? The height of this is basically goes from the x-axis up to my curve f of x. So in this case, my height is just simply f of x, right? So the farther right I am, the bigger the height is, which is absolutely the case. So what is the surface area of that cylinder? Is going to look like this. Looks like this, but this is f of x for my height, right? That equals my height. And then we have this right here is our base. And what is our base? So the base is actually the circumference of a circle, right? So this is a circumference of the circle. And what is the circle? Well, the radius is over x, right? So that's a radius, and circumference of a circle is 2 pi times the radius, right? 2 pi r. So instead of 2 pi r, it actually is 2 pi times x. So basically the area of this thing, the surface area of this, or the area in this case, would just be 2 pi x times f of x. And then what we want to do is we want to add up all of those little paper thin cylinders that we're setting in. And so we have infinitely many of them, from very tiny radiuses to bigger radiuses. But once again, I kind of mentioned this before, we only want to go from A to B. So in this case from 0 to 3, because otherwise we would end up adding double the cylinders that we need if we went from -3 to 3. So basically just going to the right from 0 to 3 ends up with the tiny cylinders in the middle, and then getting bigger and bigger and bigger will take care of all of that volume here. So in this case, to solve this one, this would be, the volume would be given by 2 pi times the definite integral from 0 to 3 of x times f of x, which in this case is x squared. Once again, we're not quantity squaring it now. This was f of x here, so it's totally different, because this is 2 pi x times f of x there, and we're adding up all of these from A to B, right? So anyway, with respect to x. So figuring this out, we've got 2 pi and then x cubed over 3. Excuse me, that's x cubed. So the antiderivative of x cubed is x to the 4th over 4, right? And then we're going to evaluate that from 0 to 3. So doing this, I can cancel the 2 and the 4. And so we'll get pi over 2 times, when I plug in 3, I've got 3 to the 4th power, which if you don't know, that's 81. You might think of that as x squared times x squared, and 3 squared is 9. 9 times 9 is 81. So anyway, and then plugging in 0, we get 0. So pi over 2 times 81 minus 0, or 81 pi over 2 cubic units would be the volume of that. So once again, the cylindrical shells method is nothing more than rotating a continuous function with the region that's bounded when it's entirely on or above the x-axis. So if you could take the area nicely like we did before, but then rotate that around the y-axis, basically we can just put a bunch of different cylinder shells in there that we can come up with those areas. And if you're thinking about this with you know, a little bit of width to it, so tiny volume here, a little bit of width to that paper, it'd be delta sub I x, and then take the limit as the norm of the partition goes to 0, right? Make that width smaller and smaller and smaller. So a bunch of paper thin cylinder slices there, starting in right here at the origin and getting bigger and bigger and bigger and bigger and bigger, and then adding them up from here to here, which actually takes care of both sides, would ultimately give you the volume. And so this cylindrical shells method is a nice alternate method that ends up adding, remember, the antiderivative is a sum. So instead of having the 2 pi x f of x inside, we can pull that 2 pi out, but we've got the x f of x in there, so just knowing where this formula comes from is going to help us remember it, and in the next video I'll give you a couple examples that we can utilize it even more.